Hello everyone, welcome back to another GIS statistics lecture video. And in this lecture video I want to talk about something called a semivariogram. And the reason I want to talk about semivariograms before we jump into Kriging is that Kriging sort of relies on this idea of a semivariogram. And again, just like what we've done before, I want to take this word and break it apart. So we have semi and variogram. So variogram, right, this vary, right, this refers to variance. Right? This is a graph of variance. Right? Semi means partial. So we're basically making a graph of partial variance, right? That's what a semivariogram is doing. And before we talk about the equation, I just want to lay down a sort of thought or a conceptual framework for what we're hoping to see. If we have points that are close together, and then we have some other points that are farther apart, and we have this point right here. So this is our center point. Right? If we were to look at the values of these points here, right, we would expect, based on, again, Tobler's first law of geography, that the variance, right, the variance of these points would be lower. If we were to go out and measure the variance of these points, right, they're farther apart. So if we were to measure variance of these points that are farther apart, we would expect that variance to be higher, again, because of Tobler's first law. Things that are farther apart are expected to be less similar. So what you would hope to see here is that as you increase the distance, right, as you increase the distance, not this, as you increase the distance, between points, you decrease the similarity in their values, meaning that the variance of those points would be higher. Now, hopefully, when we're thinking about this, you're thinking about this in, we can draw some parallels to the idea that we talked about with Ripley's, or not Ripley's K, with kernel density estimation, with kernel density estimation, where we had these bins that we went away from a point that determined their influence, right? We can do the same sort of thing here, where if we have, on this axis, we have variance, or some form of variance, right? And this is distance, right? When the points are really close together, we would hope that they have a really low variance. But as we start to include points that are farther and farther apart from each other, right, we would hope that the variance would start to increase. And eventually you'd get to a point where the variance doesn't increase anymore because you've captured the variety of the data set. So your variance would sort of plateau like this. Right? This graph comparing variance to distance, right, this is called a semivariogram. Right? Again, this graph showing variance to distance, this is your semivariogram. So again, conceptually, what we're getting at is that points that are closer together, when you measure their variance, they're going to have a smaller variance because you would expect nearby points to have similar values. as you increase the distance between the points, you would expect that variance to go up because things that are farther away tend to be more dissimilar. And then you would eventually hit a point where the variance plateaus. So we're going to come back to this diagram in another video. We're going to explain more exactly how we calculate what actually goes into this graph in the next video. But I want to just take 5 minutes to give you sort of a groundwork foundational concept of what a semivariogram is trying to do and sort of the idea behind it, relating it back to Tobler's first law of geography. So hopefully this made sense. If this diagram doesn't make sense, don't worry. We're going to look at a lot more examples, but hopefully you understand conceptually the idea here. If you have any issues with anything, I encourage you to pause the video, go back, rewatch the parts you're confused about, and as always, please reach out. Thank you.